that this type of arrangement, I am trying to tell you that how that meteorological parameters are varying within the crop canopy system. Perhaps you have already done different courses on the general circulation, different monsoons, just like secondary circulation as well as tertiary circulation. And there, some of them are at the planetary level, some of them are in the state or country level, but at the field level, what is going to happen when we are getting the radiation, when we are getting the temperature, so how it is distributed, how it is utilized by the crop itself. So let me share that. So is it visible? Anybody? Please. Yeah, of course. That I'm. Yeah. Okay. So the crop micrometeorology. Today's topic is crop micrometeorology, and thank you, Dr. Chattopadhyay, for nice introduction. So what we will cover today, that how the temperature, humidity, vapor pressure, wind, and carbon dioxide, all these components are distributed or varying within the crop canopies. What are the energy balance over crop surfaces? Then radiation distribution and utilization by plant communities. That will be just through that power interception, photosynthetically active radiation interception and radiation use efficiency. Little bit I will touch about the instruments, and ultimately what are the applications, that is that microclimate modification. So let us start with very basic, what is micrometeorology? It is a branch of meteorology which deals with the atmospheric phenomena and physical processes which are taking place or which are restricted to very limited region over the crop surface or over the earth surface or over the ocean surface. When it is over the crop surface, we used to tell it as crop micrometeorology, and it used to study the immediate atmospheric environment. Just you think that that is the within few meters of the surface. So it is within few meters of the surface surrounding crops. And in case of tree or agroforestry system, so forestry and agroforestry system, it may be about 10-15 meters like that. Now, there are the focuses on energy, water, and carbon dioxide exchange that comes under the purview of this micrometeorology, and it analyzes the vertical profile of wind, temperature, and humidity within the plant canopies. And why these are needed, that vertical profile? To optimize that irrigation, that how much that this particular soil is drying up, to enhance the yield, and to manage the pest dynamics, as already told by Dr. Chattopadhyay sir, that for the pest dynamics also there is a need of that micrometeorology. Now, first I'm starting with the distribution of temperature, humidity, and all these things within the canopies. For example, it is our crop canopy, and within the crop canopy, actually, that air, wind flows. So wind, for example, this is the wind direction. Anybody, can you see that cursor?
Yes, sir.
So this is a wind direction. Now, that some of the movement of wind may be towards upper side and some are coming towards the lower side. Now, once it is coming from the surface itself, it will take up the humidity. That is one of the important component which is coming out of the transpiration processes. It will take up the whatever that uh, carbon dioxide, some amount that may go upward, temperature may go upward, so methane may go upward like that. And there are some which are coming towards the surface. Then similar these things are also all the components, all the parameters can come towards the surface. Now, when we are talking about the movement of wind, there is a common term. The common term is known as flux. Flux means the amount of energy or amount of any material which moves per unit cross-sectional area per unit time. So per unit cross-sectional area per unit time, how much is going through this portion? So that is the flask, and it depends on the number of things or number of materials or amount of materials, amount of energy which is crossing that area, size of the area. A field may be smaller one, field may be larger one, forestry may be small forest, a very big forest like that. Then what is the time that to it takes to cross that area? Some wind movement will be very fast, so the time taken will be very less. Likewise, so the flux is the main thing which determines the upward and downward flow, which is known as that eddy current. So eddy actually that has the three-dimensional components. It includes a vertical wind component as well as that vertically upward or vertically downward. Generally, air moves, air flow is that horizontal flow, but eddy actually that upward and downward. Now, that there will be, if that air is coming from upward to downward, for example. So here we can measure that concentration of for a particular, for example, carbon dioxide you take. And here also we can measure carbon dioxide. So if we have that sensor, that how much carbon dioxide is coming from here to this portion, and if we are having that sonic anemometer in two levels, so we can tell that this much of air current is coming with this type of concentration. So that is the eddy current is moving upward or downward. So on that basis, actually, our eddy covariance tower is constructed, and I'm coming afterwards after that energy balance, that how that eddy covariance tower is operating. Now, if we think about the distribution of temperature, so all this distribution, temperature, humidity, all these parameters, they actually create an unique microclimate. And that microclimate for a particular area that differs from the other area. So there will be some gradients here, there will be some variation, and that plant structures, leaf density, their orientation, solar radiation, transpiration, all actually govern this microclimate. Now, if we think the temperature profile, that upper canopy, it actually receives most of the solar radiation. So whatever that upper canopy, that canopy is the warmest thing, warmest area, and the lower canopy actually that is little bit cooler. And at the night time, that canopy itself, it utilized as an insulator. So here that this area, that near the vicinity of the soil surface, here it will be warmer than the open air. Here it will be cooler. So at night time it will be totally different. And based on that, whatever that energy system, energy flow, whatever that sensible heat flux, that also different. Now, if we come to the humidity, so within that lower portion of a crop, that shaded portion, that actually acts as a moisture trap. And at the lower portion, the relative humidity is more than the upper canopy. Here, the relative humidity is more than the upper canopy. So, if we see the wind profile is another important thing, because wind is the carrier of all the temperature, humidity, carbon dioxide, methane, all these things. So if we see the wind speed, so it will actually, wind will start up to this portion, that speed will be almost zero. And after that, it will just take a peak and it will exponentially, it will increase. So wind speed decreases sharply within the upper canopy. So if it is the canopy, then within that canopy, wind speed decreases and it is almost zero at the near the soil. Now carbon dioxide distribution, how it happens? The photosynthesis, that actually canopy, that reduces the carbon dioxide concentration, and acting, that crop is acting as a sink. And night time, that soil, that crop, they will respire, and for that carbon dioxide concentration is higher near the ground. So that is the thing, that carbon dioxide is also, there is the difference of distribution. But how we can measure the distribution, that is the main thing. Now look at this table. These are the variables I have already told. One is temperature, relative humidity, wind speed, carbon dioxide. So at the lower canopy, that is relative to the top canopy, so here it is cooler, temperature cooler, relative humidity higher, wind speed at the low portion is very low, almost zero, and carbon dioxide at the night it will be higher. So these are the conditions which are prevail in the crop canopy system or in a micrometeorological system. Now, what are the factors influencing these type of distribution? One is leaf area index. So LAI, if the LAI is high, very big leaf, so it increases the, say, it gives a shade compared to smaller one. Then if it is that towards not horizontal, it's vertical type of leaf, then it will give less shade. So its orientation, orientation of leaf is also another important thing. Then canopy height, taller canopies, that can create a steeper gradient in temperature, taller canopies. Then transparency, canopy openness, how it is opening. For example, if you are having, say, that rice field, wheat field, they are little bit one type. And if you are saying that some pea, green gram, all this type, soybean, their that canopy openness is different. So these are the factors influencing the distribution of all the parameters. Now, the most important thing is that wind. So if we can see that if it is that wind and if it is the height, this is soil surface. So anybody, can you see this mark, red mark? Can you see?
Yes, clearly.
Okay. So if it is near the soil surface, and if it is the crop. Now, for example, here there is a big canopy. Here it is a big canopy. Now, based on big building, now that wind which is coming, for example, wind is coming from this direction, and there is a big building. So based on that, based on its height, there is a certain height up to which there is, due to obstacles of trees and buildings, you will not get any wind speed. That is, you will get zero wind speed. And so we are that these plane, we are displacing it. We are displacing the plane. So when we are displacing the plane from here to the portion, this is as plane displacement. And the D or displacement D terms. So that D is very means that magnitude of D is very high compared to another term that is known as roughness length. That is known as roughness length. So these are actually very much confusing. That's why I'm telling you again that D is actually if there is any tree or building due to this obstacle, that there is some displacement up to which the wind speed is zero, and generally it is that 1/3 or 2/3 of the average height of the obstacles. So if that height is, for example, this height is 30 meter, so our D will be 20 meter. So very high. The D amount is very high. If the crop, this crop height, for example, it is 1 meter. So this D is 0.7 meter. 0.7 meter. Now, here within that crop canopy, here above the crop canopy, this portion actually not even. This portion is not even, there is uneven thing. And due to unevenness, in the next day, that there is some drag force. Professor M.K. Nanda will cover this portion. You just be attentive on the Saturday class. So due to this unevenness, there will be again some height for which you will get very limited or zero wind speed. That is the effect of roughness of a surface, and that is known as roughness length. So after this D plus Z0, we are getting this wind, and that wind is that with the log value it is increasing. So whenever you have to calculate that wind speed at a particular height, so wind speed at a particular height, you have to give this equation, that is the U star, that is the friction or shear velocity, divided by that von Karman's constant K ln Z minus D by Z naught. Z means height at which we are measuring this. For example, if it is 2, then we are taking that wind speed at 2 meter height. So in that way, we can measure this wind speed. Here also you can see that U is equal to U star by K log Z minus D by ZO. So ZO is nothing but our surface roughness. So if it is 2, if it is 0.7, so 1.3. If it is, for example, Z naught will be very less. Z naught will be for a cropland, Z naught will be 0.1 to 0.25 meter. So it will be, for example, 0.1 meter. So for that, you can get the wind speed at different height, and k is value is 0.4. So we can measure the wind speed with the equations for different heights, wind speed at different heights. Okay. So, for example, if over the crop surface up to this is 1 meter, what will be the wind speed at 20-meter height? How can you calculate? So, with this type of equation, we can make that here that z will be this 20 meter. Now, coming to the next thing, that is the surface energy. So, just forgot something. Acha, one thing I forgot. That is, if that smooth surface, then roughness length is very less. Open grassland over, it is little bit smoother. So 0.03. Here cropland here, and if it is forest, then our Z naught is very high. So likewise, our that is varying, and based on that, that wind speed is also changing. Now coming to the surface energy balance. Now, I think that radiation component is already covered by any scientist. Still, I am just repeating this thing little bit. When we are having that incoming radiation at the surface, that is mainly the short wave radiation, and our outgoing radiation from the surface, that is long wave. That is known to everybody by this time. And that incoming minus outgoing, we are getting that net radiation. Now, that once that net radiation is coming to the surface, it is just divided into that different heat. One is sensible heat, another is ground heat, another is latent heat. So once that sun, that is the source of energy in the form of radiation, when it is coming, that maximum amount of energy plus that heat up the surface soil, and through the surface there will be that ground heat flux. Then there will be some moisture which is going upward, that will be the latent heat flux, and there are some flux which changes the temperature with height, which is known as sensible heat flux. I'm coming one by one. You just see that net radiation, so incoming minus outgoing, that is the net radiation. What it will do, the total of net radiation, this is, you can tell it Rn, net radiation. Okay. So that net radiation, some of it will just go into the soil. It will warm the soil. So if here the temperature is T1, here if temperature is T2, so T1 in the morning will be warmer, T2 will be less warm, cooler. So from T1 to T2, that energy will flow. T1 to T2 energy will flow, and it will give the soil heat flux. So we are having some soil heat flux which can be regarded as Z, for example. Then there are some of this energy that return to the atmosphere and warming the air. That is known as sensible heat flux. And some are used for the evaporation of water, that is known as latent energy. So this equation is very much important. Rn plus is equal to Z plus S plus Le, or you can write that Rn plus Z plus S plus Le is equal to 0. So you can take all this in one side, whether it is plus or minus. So it will give you that some zero amount. Now, this is the energy balance equation, Rn plus G or Z. In some book you will get the term Z, Rn plus G plus H plus Le, it is equal to 0. Now, how it behaves in the daytime and in the night time. Here, one thing actually is means for the calculation part, whatever we are getting at the surface, whatever is added to the surface from soil, it is added, something is added to the surface, or from the outside it is added to the surface, we take it as positive, and which is, so it is positive energy, and if it goes away from the surface, it is taken as negative. So coming towards the surface is positive, going away from the surface is negative. Now net radiation Rn, it is coming towards the surface in the morning time because we are getting sunlight. So Rn is positive and the latent energy, it is going upward. So evaporation, that evaporation moisture that is going upward, then the sensible heat that is going upward, and G, that is ground heat flux, that is going downward. So here you see Rn is greater than 0 and Le, H, G all are positive, all are negative. These three are negative. So all these things, if you equate, that will make nothing but 0. So Rn plus G plus H plus Le, because these three are negative in the morning, Rn is positive. So all these things, if you equate, it will make a 0. And that is nothing but popularly known as energy balance closure. So energy, that Rn plus Le, G plus H, that will be equating like that. So at night, what will happen? At night, there is no incoming solar radiation, that is not there. Only due to temperature of Earth, we are getting outgoing. So the net radiation is negative. So in the means even the evening, late evening, you are getting that minus Rn value, net radiation value. So Rn is negative. Latent energy, we are always, there is some evaporation from the surface or from the plant canopy, and it is going upward, that is going away from the surface, that is negative. But the H, sensible heat flux, so that sensible heat flux actually coming towards the soil surface. That means here the temperature is more, at the soil surface temperature is less, so temperature gradient will be towards that side. It is towards the soil surface. And at the night time, that due to radiation cooling, what will be the temperature of soil surface compared to a deeper surface, deeper profile? So at the soil surface, the temperature will be less. Here the temperature will be more. So at that time, that T2 will be greater than T1. So T2 to T1, there will be the gradient of temperature flow. So the G and H, they are positive and these are negative. So these are the energy balance component. And now coming to how we can measure this thing. How we can measure that energy balance Rn, H, G, Le. Any participant, is it okay for you?
Yes, yes, definitely.
Okay, okay. Thank you. So now if you have AD covariance tower. It's well and good, fine, but it's very lakhs of rupees, means thousands of dollar it costs. So how we can make this type of energy balance study over our crop surface? Let us see this one. If you are having that over the surface, if you are having one, for example, uh, net radiation, you may have that your temperature gradient at two places and relative humidity. So if you can measure the temperature and relative humidity gradient at two places, for example, 50 centimeter, half meter from the crop height 50 centimeter, and another is 1 meter height. So that means above the crop it is 1.5 meter. If you take that instrument and here you are taking that temperature and that your relative humidity gradient, then from that, with the help of Bowen ratio energy balance, you can make the, you can analyze the energy balance component. How? The Bowen ratio, there was a scientist named Bowen. He in most probably, yes, 1913, Bowen gave this thing that sensible heat flux and latent heat flux. The ratio of sensible heat flux to latent heat flux, there is a ratio. Know that H, that is sensible heat flux. How you can calculate that sensible heat flux? So no need, because it is a training program. It is not a particular that sensible heat flux. If we know that temperature gradient dt by dH is the, that our sensible heat flux is proportional to change of temperature gradient. Okay, change temperature with height or temperature gradient dt by dz. And latent energy, just like that, latent energy is our change of vapor pressure gradient. Okay, change of d by dz is the change of vapor pressure gradient. So if we know that temperature gradient and vapor pressure gradient, so that will give us the Bowen ratio. The ratio is nothing but dt by dE into some constant, and that constant is known as psychrometric constant. So psychrometric constant into temperature by change of temperature by change of vapor pressure. Okay. Now that if we know the change of temperature, change of vapor pressure, we can know the Bowen ratio. So we can measure the Bowen ratio at different, for example, different crop growth stages. Now you just see, this is our equation. Then H plus Le is equal to minus Rn plus G. That is actually, as I told, that is energy balance closure. Then H plus Le, if we divide both the side by Le, H plus Le divided by Le is equal to minus Rn by plus G by Le. So what we will get? We will get that H by Le, H by Le, but H by Le, what is it? H by Le is nothing but our Bowen ratio, beta. Okay, what is H by LE? H by LE, our Barman ratio. So Barman ratio H by LE, I'm writing this portion. Okay, H by LE plus LE by LE means 1. So 1 plus Barman ratio is the one side is equal to what happens in that side Rn plus G minus by Le. So Rn plus G by Le. Now what will happen through cross multiplication? Le will be, if Le comes to that side, so Le is equal to Rn, of course there is minus Rn plus G by 1 plus beta. So we can calculate the latent energy easily with the help of Barman ratio. With the help of Barman ratio, we can measure the latent energy easily. If you have this type of instrument setup, if you have this type of, at two places you need that radiation, that your temperature and your vapor pressure or relative humidity. From relative humidity you can calculate vapor pressure, plus you need that net radiation through net radiometer. So through that you can know that net radiation, latent energy from the soil, that temperature at two different depth you can measure that soil, and with the help of Fourier's law you can measure the soil heat flux and the sensible heat flux, just simple subtracting all others. You can get the sensible heat flux. And that actually Le plus S plus or G, Le, S, G, all will be given at different top phenophases. So how this will be helpful for you? How this will be helpful for you? Now you can know that how energy is changing, and from Le value, if you multiply it with that heat of vaporization, you will get that evapotranspiration. So you will get that evapotranspiration, for example, 80 millimeter per day, flowering, pod formation, end of pod flowering, 50% maturity, 100% maturity. So all this you will get the evapotranspiration value with the help of this type of micrometeorological study. So if you do not have that lysimeter, so with the help of Barman ratio energy balance study, you can measure the evapotranspiration in your crop field. Now coming to the flux tower. Flux tower, as I told, that is very costly instrument. So here there is one sonic anemometer, here it is another sonic anemometer. So we can know that how that wind is coming towards that side or it is coming towards upper side, and always we determine the concentration. So for example, concentration is coming, how much it is coming towards the ground and how much it is coming towards the upper side. If you measure that, if you just make that summation for a whole day, you can measure that this is the flux, and the flux of, for example, carbon dioxide or flux of methane will be this. And it is towards the soil, means crop surface, or towards the soil surface, or away from the soil surface. So that is the simple that diagram of the flux tower. Now coming to the again our crop. So a small fraction of light which is transmitted through the leaf that actually that canopy intercepts. So if there is some crop and how much it is intercepted, that mainly that photosynthetically active radiation, that gives that what is the biomass. That gives the biomass. So that whatever the crop and that degree of inception or interceptions, that depends on the density of the crop canopy, optical properties of leaves, number and size and gaps of the crop canopy. So these are the LAI, all are well acquainted. And there is another term, that is extinction coefficient. So here, that if we are getting the transmitted part and if it is that intercepted part, that is governed by the leaf area index as well as that extinction coefficient. Now this portion is very much important, that how, especially for that those who are working with that crop sciences, agronomy or other subjects, plant physiology, all they are very much well acquainted also. So but in case of PAR, how we can measure this? For example, here if we keep that instruments and here we can keep that instruments. So it is coming, whatever that PAR we are getting above the crop surface, that is our I naught. And what we are getting that below the crop surface, so there are some crop. Here it is that I T. This is I T. So this is transmitted, this is our incoming. And this is governed by this equation, IT by I naught is equal to e to the power minus. This is the nothing but our Beer's law. This is nothing but our Beer's law. So there are two important terms. One is intercepted part, I par, and another is absorbed part. So in case of intercepted part, only we used to take that part above the canopy or incident minus part which is transmitted. So this reading minus this reading will give us that intercepted part or I par. But for the absorbed part, there are that part above the canopy which is coming towards the surface, part reflected from the soil, it is coming towards the surface. So these are added. These two are positive. And which are going out, the part transmitted, part that is transmitted is going out, and part reflected from the vegetations, that is going out. So these four components are giving to that absorbed part. So absorbed part is much more precise. The value of absorbed part is little bit lower than the intercepted one, generally. Now there is one instruments, coming to the instruments. This is our line quantum sensor. The line quantum sensor here that gives it within that crop, if we give, then we are getting that transmitted part. And here above there, we are getting the incident part. So if we are having these two, with the help of equation, we can measure that LAI. So that SunScan probe, I don't know whether you have this type of instruments in your university or institute, but this is very good instruments which will give you that intercepted part, then extinction coefficient and LAI all together. All together, that is, and generally that for that part we used to use that line quantum sensor. Now, if we are having for a particular crop growth period, if we are having that absorbed power, cumulative absorbed power, and that biomass are different. Huh? Accumulated biomass versus accumulated absorbed power. So we will get this type of this once there will be power will increase, accumulated power, the biomass will also increase. So this. So there will be, we will get this type of dotted some data, and from that we can get that straight line equation, which will give the slope of that, line will give us that radiation use efficiency. Generally, radiation use efficiency means how much amount of radiation is needed per unit production of biomass. So that these divided by biomass divided by part will give you that radiation use efficiency. So this is another thing, and this radiation use efficiency means here what is the y is equal to mx plus c. Now this m or slope, that will be the radiation use efficiency. So for that, what is the cultivar? Here radiation use efficiency is highest for this cultivar. So we can utilize this to get best uses of radiation. So this type of work you can do with the help of this type of micrometeorological study. Now, if you don't have that, your line quantum sensor, so what you can do? If you can have that BSS data, bright sunshine hour data, from that you use this Angstrom equation, you can get that global solar radiation data. And from that global solar radiation, there is one multiplication factor. Generally, it is 0.48. So if the GSR is, for example, 20 megajoule per meter square per day, so 20 into 0.48 will give you this incident power. Then you are having that LI and K value from the secondary data set from the referred literature. So you utilize the Beer's law, you will get the intercepted power. And just you validate, and that intercepted power you can utilize for that radiation use efficiency. So that you can derive the power use efficiency from bright sunshine hour data. Determine that radiation use efficiency using sunshine hour data. So that is very important protocol which we develop for determining the radiation use efficiency if you don't have intercepted power. For example, in your university, you don't have that line quantum sensor, but you want this type of work. You want to know that radiation use efficiency. So through that method, you can utilize, you can use. And for here, that due to time constraint, if there is anything, any doubt, you just mail. I will just explain, no problem. Now there are other instruments. That pyranometer is very important instrument, which is used for solar irradiance. Pyrheliometer, that is for the direct solar radiation. Pyrgeometer, that is for the infrared radiation. So these instruments are very much important for use. That is the pyranometer. That here pyranometer, here the thermopile sensors are there in this portion. So this thermopile sensor it will, due to that radiation, it will give rise to that, due to thermoelectric effect, the temperature difference will give you the what is the amount of radiation. Then these are the peer heliometer. So with the help of solar tracker, it will always in the direction of solar light towards the sun. So the direct solar light come through that and give the direct solar radiation. So there are direct solar radiation and diffuse solar radiation. So you will get the direct solar radiation from this and total radiation with the help of this instrument, and this instrument's reading minus this instrument's reading will give you the diffused radiation. Now I'm coming towards the last portion. This is the microclimate modification. This is the microclimate modification. So how we can modify our microclimate in the field? So we can control our heat load, we can control the wind speed, improve the water balance, we can modify through our cropping system through tillage. But that should be done before that crop season starts. So controlling heat load, heat trapping you can do, heat evasion. So heat trapping, that row spacing, orientation, mulching, greenhouse, burning of crop residues, which is not at all recommended, of course. So with that help, you can trap your heat. But heat evasion, that is done by the shading, increasing plant density, this. Now wind speed, this is very well known to us, wind break, shelter break. Now water balance improve means all the our parameters or input parameters must be changed according to such a way that it will give our, that positive balance will be more. So it should reduce the evaporation. For reducing evaporation, use of mulches, then cultivation of crops, then infiltration, that tillage, then row to row spacing, that must be there, increasing, that will give you more infiltration, and modification of transpiration, that is the use of that anti-transpirant. And there are some specific modification like greenhouse structures, temperature increase, protection of frost, sprinkling the canopy with water, or in the our summer season rice, means the Bodo rice, popularly known as. For that we used to, in the nursery bed, we used to just irrigate the nursery bed at night time, and in the early morning we used to drain out that water, and again at the night time we give that irrigation, so that the temperature of water, or water as the specific heat capacity is high, so it can retain the temperature. That is the thing. So this is the microclimatic modification. So you know, you are well aware this of the how it is that trap heat, how that wind belt is using, and I am giving simple that our micrometeorological modifications in our that Nikra village. So here, for example, that these are the crops which will be grown in the winter season, and towards the north, if we just give this type of cell belt, and here we can grow some just cucumber like some vines, so it will make the layer, so that the inner that rows will not get so cold temperature. So at just after that October season, it is done like that, and at the end of December, this will be fully covered. Now that water, to prevent that evaporation from the small water surface, they are that band of the water, the band, two sides band, they are growing these type of crop, this type of that crop which need the scaffold. So that net is using as scaffold. So for that, over this net there will be that uh, uh, that pumpkin or bottle gourd is are grown. This is bottle gourd. So once they grow that bottle gourd, they, with the help of small boat, they go inside this dense cover and they just harvest this bottle gourd. So these are the examples of microclimatic modification through which you can conserve your natural resources. Now, at last, how these are actually related with all these things. So once what we read today, these are actually we read up to this zone. Now that micrometeorological modification may be connected with the changing environment, with the climate change, with the solar dimming or solar radiation, high solar radiation, the aberrant meteorological conditions, linked with it can be linked with all the our measurement processes, slope of the field, soil properties, then what are the crop characteristics, what are the crop management practices, abiotic stresses, biotic stresses like pest, diseases. So these all are related with micrometeorology. So this is already 4 p.m. and let us stop here. Thank you. And right now, actually, there must be one class for you that how you can use the new techniques, just like machine learning, in case of predicting the micrometeorological parameters. For example, net radiation, that is high costly instrument. In the Indian rupees, it is more than 1 lakh rupees cost. But if you have some other canopy temperature data, solar radiation data, or bright sunshine data, so you can easily calculate this thing. So these are the means future of micrometeorological study. So thank you all. Yes. Yes.